Good afternoon, scientists. This is Mrs. Geis, and today we are going to be starting a brand new unit called Properties of Matter. So you're going to take out your brand new red LearnEd notebook entitled Properties of Matter. And please note that your teacher will go through the unit organizer with you, the vocabulary, the pre-check, and the post-check at the end of the unit. Your teacher will also go through the bell ringers with you, doing a few each day. So go ahead and open up your notebook to page 6, and we will get started. So what is matter? You've probably learned that any physical substance that composes materials in the natural world, that is what we define matter to be. The fundamental unit of matter is the atom. We know that atoms are made of 3 different types of particles. They are made of protons, which have a positive charge. They are located in the nucleus, and their mass is measurable. They are made of neutrons, which have a neutral charge. That means they're neither positive or negative. They are located in the nucleus as well, and their mass is measurable. And then finally, the third part is the electron or electrons. Their charge is negative. Their location is orbiting around the nucleus, and their mass is negligible, which means it is very small and very difficult to measure what little mass they have. So most of the mass in the atom comes from the proton and the neutron. The charge, that is related to the number of protons or electrons in an atom. The charge of the proton is equal to and opposite the charge of the electron. A neutral atom has an equal number of protons and electrons. They kind of cancel each other out. The atomic number, and we'll refer to this a lot when we're referring to elements on the periodic table of elements, but the atomic number is the number of protons in an atom. They are located in the nucleus. The mass number is the mass of the protons and neutrons in the nucleus of the atom. Elements. So we'll be talking a lot about the periodic table of elements, but it's important to know what an element is. An element is a building block of matter. It can't be broken down into anything simpler. The periodic table has over 118 elements represented. Here we have, for example, hydrogen, which is the first on the periodic table. This is what the hydrogen atom looks like. And compare this to the helium, which is located across from hydrogen on the periodic table. And you can see the difference. Look at the nucleus and check out those electrons. There's quite a big difference here. We'll go into detail some more in just a moment about those. So we said that there are about 118 elements represented on the periodic table of elements. About 26 of these are found in living things. And it's also important to note that elements are represented by chemical symbols. So for example, the letter C represents the element carbon. The letter K represents the element potassium. A compound is when we have 2 or more atoms chemically combined. The most common compound, and one you have heard of probably quite frequently, is H2O. This is what H2O looks like. We know that H2O is the compound of water. It is 2 hydrogen atoms plus 1 oxygen atom. Here are the hydrogen atoms. Here is the oxygen atom. When you don't see a subscript after a symbol, you know that it means 1. Okay, and when you look at H2O, think of Mickey Mouse ears. It's kind of what it looks like. When combined in a compound, elements change properties. So, for example, let's look at salt, table salt for a minute. This is Na, which stands for sodium, which is a metal. And then we have Cl, which is chlorine, which is a gas. When they're combined, they form table salt, which is sodium chloride, and it is written as NaCl. Separately, again, Na is a metal all by itself. Chlorine is a gas. We certainly don't put metal gas on our food to season it. So when they combine, we form something completely different, and that is table salt, sodium chloride. So they are represented by chemical formulas. For example, H2O, the symbols of the elements followed by the ratio in which they occur. So here we have 2 hydrogen atoms, 1, 2, and 1 oxygen atom right here. We don't see anything in the subscript, so we know that means there is 1. And this is what a water molecule looks like. There we go, H2O. Here are some common formulas. And again, we've talked about H2O, water. But we also have C6, that means 6 carbon atoms, H12, 12 hydrogen atoms, and O6, 6 oxygen atoms. When combined, when these elements, 3 separate elements, carbon, hydrogen, and oxygen, are combined in this manner, we get glucose. We know that glucose is a product of photosynthesis. We know it as sugar used for fuel. Here we have Na, which is sodium. We have O, which is oxygen. We have hydrogen. When they are bonded together, we have sodium hydroxide, which is a very strong base. Here we have Na, again, which is sodium. We have Cl, because elements, it's important to note, they always are an uppercase letter followed by a lowercase letter. So Cl stands for chloride, and then O, which is oxygen. When these are combined together in this form, we get bleach, which is again a very strong base. A molecule is a single unit of 2 or more atoms combined chemically. So, for example, 2H2O equals 2 molecules of the compound H2O, which we know to be water. Now let's talk about mixtures. Mixtures are combinations, mixed combinations of at least 2 different substances. These substances keep their own physical properties. So unlike the compounds where they're chemically changed, mixtures keep their own physical properties. They are combined and they're physically mixed. Mixtures can be separated. They can be filtered and evaporated. How may these techniques separate a mixture? Well, think about it for a minute. If we have salt water, right, that's a mixture. We know that we can evaporate the water and the salt is left behind. Very small filters may even be able to filter out the salt particles. There are 2 types of mixtures, homogeneous and heterogeneous. Homogeneous have equally sized particles. These are also known as a solution. Heterogeneous have differently sized particles. In a homogeneous mixture, it looks evenly distributed. Can you think of an example? Have you ever mixed some Kool-Aid mix in water? You take the Kool-Aid mix, you take the water, you mix them together, and then you can't tell what is the water and what is the mix, right? It all looks the color of the Kool-Aid. That would be powdered drink mix in water. Heterogeneous doesn't look evenly distributed. Can you think of an example? For example, have you ever mixed sand and water? You shake up the jar really well, You can see it swirling around, but you can definitely distinguish between the sand particles and the water. Once you leave it sitting for a while, the sand will fall to the bottom, the water will stay at the top. Here's another example, Italian salad dressing, right? You shake it up. It looks, you can kind of see all the different parts of the salad dressing in there. You can see the seasonings, you can see the oil, you can see the vinegar. And especially when you let it sit for a while, it definitely will separate out. That is a heterogeneous mixture. Remember, homogeneous looks the same, homo means same, heterogeneous means different. You can see the different particles and they will definitely separate out. So let's talk about chemical bonding. Chemical bonding occurs between electrons of different atoms. How they form? Well, electrons are shared or transferred. There are two primary types of bonding, covalent bonding and ionic bonding. Let's talk about those. In covalent bonding, we actually have the sharing of electrons between atoms. Here's an example, CO2, which is carbon dioxide. Okay. Here's another example. We have two hydrogens and one oxygen, right? Can you see how the electrons in the outer shell are being shared right here? They overlap. An ionic bond is when we actually have the transfer of electrons between atoms. So they actually go from one atom to another, from one orbit to another. So here you can see where this electron in the outermost shell has been transferred over here. You can see the transfer right here. It goes from here to here. All right, now let's get into the periodic table. The periodic table is a way for us to organize the elements that we have identified. There was a scientist named Dmitry Mendeleev. He was Russian. We use his work today because we consider him to be the founder of the modern day periodic table. What he did was he looked at traits or characteristics of different elements, and he arranged them according to those traits or characteristics. On the periodic table, we have horizontal rows going across. We call those periods. And there are 7 periods going across in the periodic table. We also have what we call groups. These are the vertical columns in the periodic table. We have 18 groups, and they are based on similar properties. So when you know when an element is in the same group as another element, they're going to have something in common. So let's talk about the history of the periodic table. There's a spot in your notebook where you can summarize the following information. You may also conduct your own research, and we'll be talking about Dmitry Mendeleev a lot during class. But basically, in the late 1700s, scientists began grouping elements and attempting to organize them based on their properties. Remember those characteristics that they have? So it wasn't until Russian chemist Dmitry Mendeleev developed his original table that it became widely accepted. This table is seen in your notebook. There are many different properties of the elements on the periodic table, so they are grouped into 3 main categories: metals, metalloids, which is a combination of metals, and nonmetals. You will be working in class with your teacher to complete the chart on page 8 in your notebook. Do some research and also see if you can find some additional properties. In class, we'll be discussing reactivity, properties, and examples. So again, we have metals, metalloids, and nonmetals. We're going to discuss the reactivity of each of these groups. We're going to discuss the properties that they have, and we're going to give examples. Let's talk about the symbol in the periodic table. Each element has a symbol. This is how we name the elements. And the symbol is named, as I mentioned earlier, with an uppercase letter and a lowercase letter next to it. Some of the elements only have an uppercase letter. So this is sodium, Na. Whenever we see Na, we know that we're talking about sodium. We also have the atomic mass. The atomic mass is the number of protons plus the neutrons. Oftentimes, it will be in a whole number plus a fraction or a decimal. The atomic number is very important. The atomic number is the order on the periodic table, and it is based on the number of protons in the nucleus. You know that when you see an element and the atomic number listed, usually in the upper left-hand corner, you know right away the number of protons in the nucleus. And the state of matter at room temperature, the physical property. And this differs depending on the element. But remember, when we're talking about the state, we're considering it at room temperature, the state of matter at room temperature. Now let's talk about valence electrons. Remember, electrons are the little orbiting particles that orbit around the nucleus of the atom. These are located in the outer shell. There are the number of bonding electrons. There are chemical symbols, which show the Latin origin, usually. And then chemical formulas are constructed from each element composing the compound. This is a lot to take in, so we will be discussing this in class in a lot more detail. Naming the compounds. So remember, when we combine elements together, when they're chemically combined, they develop a new name. The rule that we go by is we use the symbol followed by the ratio in which that element occurs. So here are some examples. NaCl. We have sodium and chlorine. Remember, a metal and a gas. When they're combined, we get sodium chloride, also known as table salt. Here we have carbon, hydrogen, and oxygen. 6 atoms of carbon, 12 oxygens, 12 hydrogens and 6 oxygens. When they are chemically combined, we get a brand new substance called glucose. H2O, can you guess that one? 2 hydrogens and 1 oxygen, we know as water. H2O2, very similar, but you got that 1 extra oxygen atom there. That gives us hydrogen peroxide. Again, a very different substance. You wouldn't want to mistakenly drink a glass of hydrogen peroxide instead of water. That 1 atom makes a huge difference. Here we have Na, so we know that to be sodium, O, oxygen, H, which is hydrogen. When they're combined, they create a very different substance called sodium hydroxide. And then finally, here we have H and then Cl. Remember, I said if it's followed by a lowercase letter, we know that's 1 element. So 2 elements, hydrogen and chlorine, combine together to give us hydrogen chloride. In class, we're going to be researching 10 different compounds. We're going to provide their chemical formulas. All right, let's look at this periodic table now. I've been talking a lot about it, but here we go. And you have a wonderful color copy in your book which is found on page 10 and 11. So the periodic table, remember I was telling you guys, they are listed. We've got columns. And if you look at this, do you see how the colors, they're color coordinated, right? So we've got, these are called groups. We've got group 1, group 2, groups 3 through 12, group 13, group 14, 15, 16, 17, 18. When we go across, these are called periods. We have 7 periods. So this is the first period, the second period, the third period, 4th, 5th, 6th, and 7th. And remember I said that you can look at each box and you can get a lot of information from this one little box. So this is, example, this is oxygen and it's enlarged for you so that you can see it. Up here, we have the number 8. So the atomic number is 8. That means there are 8 protons in the nucleus. The symbol is an uppercase O. We also have the name, oxygen, and then the atomic mass is up in this. Sometimes you will also see that referred to as, as the weight. Sometimes we say atomic mass, sometimes we say weight, but I just want you to be familiar with that. Okay. All right, let's look at what these have in common. So group 1, these are alkali metals, the purple here. These are very reactive and they are not freely found in nature. So very reactive, that means they will react with water. Group 2, we have the alkaline earth metals. These are shiny, silvery, and fairly reactive, not as reactive as group 1. Now, groups 3 through 12. Notice the orange here. These are called transition metals. These are less reactive. Groups 3 through 12. In 13 through 17, groups 13 through 17, we have nonmetals. These elements do not have any properties of metals. And then finally, group 18, the noble gases. These are odorless and colorless gases. Have you ever had a helium balloon? There is helium right there. Helium is a part of the noble gases, odorless and colorless. Remember, we read the periodic table going across. So hydrogen is our first, helium is number 2, okay, lithium, and so on. We read them across and they are arranged according to that atomic number, which is the number of protons in the nucleus. Again, alkali metals, very reactive and not freely found in nature. Alkaline earth metals, shiny, silvery, fairly reactive. Transition metals, groups 3 through 12 are less reactive. Probably some easily recognizable metals in there. Nonmetals do not have properties of metals. Noble gases are odorless, colorless gases. And again, here is an up-close look at what an element square looks like. So it's easy to see. The largest thing you're going to see is that symbol. So we have carbon here. This is the C, the one uppercase C. We know we have carbon. Here's the element name, carbon. Now this time they have the mass number down below. Sometimes you will see it here. Sometimes you will see it listed as atomic weight. But then up here, usually in the upper left corner, you will always see the atomic number. Remember, this is how the elements are arranged on the periodic table. This means that carbon has what? If you said 6 protons in the nucleus, you would be correct. Number of protons in the nucleus is the same as the atomic number. All right, you have now learned about the basic properties of atoms and molecules. There are 3 states of matter that define the interactions of these atoms or molecules. So in class together, we're going to investigate and describe these and list them on the chart on page 12. Your teacher will give you further instructions about this, so don't worry about it. I am going to show you the slides. If you'd like to pre-fill them before class, you are welcome to. Solids, and this is probably a review because states of matter, if you recall, goes way back to kindergarten where you talk about things are either solid, liquid, or gas. So I like the way that they've represented them using substances in a balloon. So we've got a balloon here and it's probably filled with water. So we can see that a solid, if it's frozen water, it's going to take on a shape. It's going to be rigid, have definite volume and shape. The atoms or molecules are packed closely together. The atoms cannot be moved any closer together in this state. Atoms are constantly vibrating due to thermal energy, but cannot be seen on a large scale. Liquids. Now we know that this is room temperature, right? There's probably water in this balloon, but they have a definite volume but can change shape by flowing. The atoms or molecules are touching, but they cannot move around. But they can move around. They are flowing, unlike in the solid form. Density is similar to solids, similar density to a solid, and it can take the shape of the container that it's in. So here the water is at room temperature. It is taking the shape. Gravity is doing its magic here, and it is falling. You can see that, and taking the shape of the balloon. All right, gases. Gases have no definite volume or shape. The atoms can spread out indefinitely. They have enough energy to overcome forces. The low density is present because atoms or molecules are not packed closely together. So these are extremely less dense than in the liquid or solid form. And they can take the shape of a container if confined to a space. Each phase change is caused by a change in temperature. Increasing temperature causes the molecules in a substance to move quicker. So for example, here's what they look like in a solid form, in a liquid form, and in a gas form. And again, this is probably a review because I know you've talked about states of matter throughout your science classes leading up to 8th grade. All right, this is cool. Check out these slow motion pictures of milk drops. How do you think these molecules are interacting? Why do you think this happens? Think about what we just discussed and talk about this during class with your classmates. All right, we will be doing the different activities in a virtual setting. So your teacher will give you more information about these. Now let's go to page 13. Let's look at this diagram here, right? We know that temperature causes the different changes. So when we have heating, we have evaporation. Remember, think of the water cycle, right? When we have cooling, we have condensation. Okay, so liquid becomes a gas when you have heating, evaporation. Gas becomes a liquid when you have condensation forming, right? When those temperatures go down. Freezing, liquid turns to solid, melting, the solid turns to liquid. Here we have the gas, we have sublimation occurring and it becomes a solid. We have deposition from the solid going to a gas. Now let's talk about physical and chemical properties of matter. So physical properties can be observed without changing chemical properties. So these things can be changed back. For example, melting, boiling point, color, density, etc. Those are all properties. And in a minute, we'll talk about physical changes, which I mentioned can be changed back. But properties can be observed without changing chemical properties in the solution. So again, melting, boiling point, color, density. Melting point is the temperature at which a solid melts to a liquid. A pure substance, it's important to note, is made strictly from one element. Here's an example, gold, and this chemical symbol is AU, uppercase A, lowercase u. Many metals are common examples of pure substances. They are made, again, strictly from one element. The boiling point is the temperature at which a liquid boils. The phase change forms a gas. We know in this state, molecules expand and move rapidly. The boiling point or temperature remains constant as long as it is boiling. An example, water boils at 100 degrees Celsius. Now let's talk about density, which is another physical property. Density is the mass to volume ratio. We know that we can calculate density because density equals mass divided by volume. Density remains constant regardless of the state. Some examples, lead, the chemical symbol is Pb, is a very dense metal. And then finally, color. Color is helpful in identifying a substance, although not completely effective by itself. A change of color is also an indicator or a chemical property. It indicates that a chemical change has occurred. So some examples, it may show a chemical or physical change. So color can show both a chemical change or a physical change. Can you think of any other physical properties? Now let's talk about chemical properties. These can only be observed by changing the chemical composition. Chemical reactions occur. That means reactants form products. They react with other substances, and the pH will change. A good way to remember it is chemical changes cannot be changed back to their original state. Chemical properties can be measured by their reaction with other substances, pH level. So we'll again do another activity together in class, whether virtually or in person. It's important to know that all physical and chemical changes involve a change in state of matter or energy. So one of these, the state of matter or energy. Physical change, change in the state related to the phase changes or changes in shape. Remember? Solid, liquid, gas. Physical changes only occur when chemical changes do not occur. It does not change a substance. Remember, chemical changes can never go back to their original state, or their original form, I should say. Here's some examples. Ice melting, water boiling, salt dissolving in water, paper shredded. These are all examples of what kind of change? If you said physical, you were correct. Can you think of any other physical changes? Chemical changes. Chemical changes occur in a chemical reaction. What is important to know is the atoms are rearranged to make new chemical structures, something completely new. Think of, remember I said salt and chlorine come together to make table salt, sodium chloride, something completely different. Reactions change the arrangement of the atoms in the molecules. We're going to be talking a lot about this in class. So let's look at this just for a minute. H stands for hydrogen. I have 2 hydrogen atoms. I have 2 molecules of this. I'm going to combine it with oxygen, with the 2 atoms of oxygen. I'm going to get 2 molecules of water by doing this. Chemical changes may cause odors, gas, formation of a precipitate, temperature, or a color change due to the energy input or output. As I mentioned, there is a rearrangement of atoms. This forms new molecules, completely new substances. A change in color may indicate a change in chemical composition. So for example, white paper turns black when it's burned. Can you ever get it back to its original paper form after the paper has been burned? The answer is no, because a chemical change has occurred. When a chemical change happens, you can't get it back to its original state. Change in temperature may change if a chemical reaction occurs. Sometimes we will combine substances and heat will form, or cold will form. So this must indicate the formation of a new substance. Example, burning wood on a campfire. This excludes the simple transfer of heat. So I have wood, I've applied heat to the wood, and my resulting substance is ash. Is this a new substance? Think about it. Formation of gas. This may occur when 2 substances combine chemically. This excludes, again, phase changes such as boiling due to temperature. This indicates the rearrangement of atoms. The formation of a precipitate. That means a solid substance separated from a liquid. That is a precipitate. So now let's start to look and explore chemical reactions and what happens during the chemical reaction and after the chemical reaction. When I'm reading a chemical formula, I like to say the element, and I say reacts with, a chemical reaction occurs. That's what the arrow stands for. And these are my brand new substances. The recombination of atoms to form new molecules. So let's try this. Let's take A and C. These are just letters. These are not elements. I'm going to take A and C, and I'm going to combine it with B. I'm going to have a chemical reaction occur, and I have now formed C plus AB. Can you see I still have all 3 of my letters, my A, B, and my C, just reformulated in a different combination? That's all there is to balancing chemical equations. We will be doing a lot of this together in class. We have actually devoted probably about 2 weeks just to balancing chemical equations. So do not stress if you don't get this the first time. It takes a lot of practice to feel confident, and it's easy once you get the hang of it. It's actually even fun. So this time, let's say I have 3 molecules of A, and I'm going to combine it with B, which now has 2 atoms, and C. This is known as my coefficient. The number in front of my element is my coefficient. That tells how many of it I have. My subscript number, my little number that's below my element, it indicates the number of atoms. Now we know the law of conservation of mass tells us that matter can never be created or destroyed. So I'm going to have the same amount of matter on this side of the equation as I do on this side. These are my reactants. Remember, the arrow is my chemical reaction, and this side of the arrow indicates my products. So I'm still going to have the same amount of matter. It's just been recombined in a different format. So here is my 3A plus my 2 atoms of B plus my C. I now have 2AB plus an AC. This will make more sense once we practice it together in class. Let's do another one. I have CH4 plus 2 of O2. These are my reactants, a chemical reaction will occur when they're combined. And I now have my products, which are CO2 and 2 molecules of H2O. It's the same on either side, same amount of matter, just recombined in a different way. Whatever is on this side of the equation, just like in math, has to equal or balance out with what's on this side of the equation. All right, so let's talk about the conservation of matter. Atoms in the reactants, remember on the left side of the equation, are rearranged to form the products. No matter is created or destroyed. In a closed system, gases are not released to the atmosphere. The mass of the products equals the mass of the reactants. Remember, because of the conservation of mass or matter, matter can never be created or destroyed. So let's take an in-depth look at the chemical equation below. I have CH4 plus 2 O2s. They're going to combine. These are my reactants. They're going to have a chemical reaction. They're combining here to form my new products, CO2 plus 2 H2O. This is methane. This is oxygen. When they combine, we get the resulting products are carbon dioxide and water. Identify the reactants and the products and use the space below to list the atoms of the elements involved on each side of the equation. So again, the reactants are the methane and the oxygen, right? When there's no coefficient in front, I know that means 1 molecule of methane. Here I have a coefficient, so I have 2 molecules of oxygen, which is O2. They're going to combine, and I'm going to be left with the same amount of matter, same amount of atoms. They've just been redistributed, kind of rearranged. Here's an easy method to do it. So let's list our reactants. I know I have 1 carbon, and I have 4 hydrogens, 1, 2, 3, 4. I have 2 molecules of O2. So here's my O2, 2 of them, but I have 2 molecules, so I'm going to do that twice. Here's my products. I get 1 molecule of CO2. There's my C. There's my O2, 2 oxygen atoms. And then I get my 2 molecules of water. So 2, there's my 2 hydrogens, 2 hydrogen atoms, but I have to multiply it by 2. 2 hydrogen atoms, right? And because whatever I did to the hydrogen, I have to do to the oxygen over here, I have 2 oxygen atoms as well. Is there an equal number of atoms of each element on both sides of the chemical equation? What do you think? If you said yes, you are correct. Let's practice this concept using a more advanced set of colored equations. And we will be doing this, set of equations. We're going to use colored construction paper, or it's fun to use Skittles. They work really well for this activity. We'll be doing this together in class. So don't worry, we're gonna kind of glide over it or pass over it right now. Okay, but we'll be doing this together in class. So here we go. The conservation of matter. We know in photosynthesis, again, CO2 plus H2O plus sunlight gives us, right? We know we have combined all of these things. These are our reactants. A chemical reaction has occurred. And what do we get? We get oxygen and glucose, right? Here's our glucose. So what is an atom? What is a compound, right? What is happening to the atoms and the compounds in this equation, right? Here's our compound, water. Here's our compound, glucose. Here's our compound, oxygen. So what is a balanced equation? Remember, whatever we do to one side of the equation, it has to be equal on the other side. Let's balance the equation using colors to represent the atoms. And again, we will be doing this together in class. We'll be using blue to represent a carbon atom. We'll be using, there we go. Here's our carbon, there's 1. When there's no subscript, just like when there's no coefficient, you know that it's 1. Over here, we have the subscript 6, so I know that there are 6, 1, 2, 3, 4, 5, 6 carbon atoms. There they are, 1, 2, 3, 4, 5, 6. I can't count. Okay. Orange is going to represent your oxygen atoms. There we go. I've got 2 on this side. How many do I have on this side? Here and here. Oops, I missed that one. 1, 2, and 6. 1, 2, 3, 4, 5, 6. And again, when we do this in class, it will make a lot more sense. And when you use Skittles or colored paper, it's great for you to see that. It's a great visual. All right, so there's photosynthesis. We have the same amount on this side as we do on this side. Even though a chemical reaction has occurred, because the law of conservation of mass or matter tells us that matter can never be created or destroyed, we know that whatever we have on this side of the equation, we also have on this side of the equation. All right. Respiration. We take oxygen and glucose. Respiration is a chemical reaction that gives off carbon dioxide, water, and ATP, which we know adenosine triphosphate is cellular energy. Again, we will do this in class. We'll talk about an atom and a compound. We know what is happening. There's a chemical reaction. They are being reconfigured or rearranged. Let's balance these. There we go. Whatever we have on one side of the equation, we're going to have on the other side. So let's talk about the conservation of matter, explaining what type of reaction is occurring in these images. What happens to the atoms? Is matter created or destroyed? Why or why not? What do you think? We have a match being lit. Definitely a chemical reaction happening here, right? So we think about the before with the reactants, the chemical reaction, and the after, which gives us the products. Here we have a marshmallow roasting over a fire. Think about what types of changes these are. Are these physical or chemical changes? Could you ever get that marshmallow back to the original state? Can you ever get the wood or the match back to the original state? Think about it. Why is it difficult to observe this law in the classroom? You can still carry out in many different chemical reactions in the lab setting. So why is this law difficult to observe? What do you think? Can we see the atoms? Not necessarily, right? You'll not be able to take accurate measurements of the mass of the products due to the release of gas and or the changes in the composition of the matter. Here's a really fun activity, and you can try this one at home. Root beer floats. How many of you guys love root beer floats? How can you observe a chemical change while making a root beer float? Well, here's how. In a plastic cup, mix 1 small scoop of vanilla ice cream, or any kind of ice cream, with a half cup of root beer or any type of soda. Using another sheet of paper, record your observations. When you combine them, describe what is occurring. Explain and answer the following questions. Number 1, which states of matter were you able to observe? Describe each one. Solid, liquid, gas? Number 2, why do you think the soda bubbled more than usual when added to the ice cream? What do you think happened? Number 3, what type of change was shown by this reaction? And how can you tell? Number 4, how might different amounts of ice cream or soda impact this experiment? If you like eating root beer floats, try it with less ice cream or more ice cream, or less root beer or more root beer, and see what happens. Make your predictions and record your results. Okay. We will be doing this on page 20, again, together in class. We'll talk about reactants and products. And then we're going to use our knowledge of the law of conservation of matter or mass to balance the equations completely. Okay, so we will be doing this together in class. Like I said, balancing chemical equations is a little tricky. And once you get the hang of it, you'll find that it's actually fun and easy to do. It makes sense. And always remember that whatever you have on one side of the equation, you have to have on the other side of the equation. They have to balance out. That's why we call it balancing equations. Do not worry. We will be spending about 2 weeks in class covering and practicing and having lots of fun with balancing equations. So that is it for your notebook. Your teacher will be giving you instructions about doing the unit review questions. I hope you have enjoyed discussing properties of matter with me today, and I look forward to seeing you soon.